All right, this is section 20.5, Bronsted-Lowry acids and bases, and we're also doing 20.6 in a little bit. All right, so here's our objectives: be able to define and identify Bronsted-Lowry acids and bases, understand what we're talking about when we're talking about the conjugate acids and bases, be able to write formulas for them and identify them, and this last one we're really not going to cover that one. All right, so first of all, we've talked before about the Arrhenius acids and bases, and most of you are familiar with that. Well, a couple scientists, Bronsted-Lowry, found another way to describe acids and bases, and for one thing, the one thing that it did greatly was increase the number of bases that were considered. It also, increased some acids, but primarily a lot of. All right, so let's kind of talk about the definition. First of all, a Bronsted-Lowry acid is one that is a proton donor. Remember, a proton, H+, that's a proton. So something giving away a hydrogen ion. Okay, that's a proton. That's an acid. Something that is accepting that proton, that's known as a base. Okay, so let's take a look. Here we've got some hydrochloric acid in water. And, if you look at the picture, you see that the hydrogen here is given to the water molecule. So this proton, that H+, is donated. So up here in the equation, this hydrogen is given to the water. So if it gives away the hydrogen, that's an acid. If it accepts the hydrogen, that's a base. So yes, in this example, water is considered to be a Bronsted-Lowry base in this example. All right, let's take a look at this one. Okay, if you look at what happens from here, from the left side to the right side of the equation, you see that it kind of lost a hydrogen. So this hydrogen was given to the hydroxide. Okay, so something that gives away or donates a hydrogen, that's an acid. And the one that accepts the hydrogen is the base. And so far none of those are any different, but I mean that's just the way that they define it. So it's just slightly different than Arrhenius defined. All right, so let's take a look at these following equations and see if you can identify the Bronsted-Lowry acids and bases. All right, so look at this one and see which one is donating the hydrogen. Hopefully you see that this one here is giving up the hydrogen here. So this is our acid. This is our base. Okay, take a look at this one. Okay, you see that the hydrogen from the HCN is given to the water. So this is the acid. This is the base. Okay, so far it's nothing too difficult. So this is a little bit broader definition, includes a little bit more. And anything that's an Arrhenius acid is a Bronsted-Lowry acid, but not the other way around. Also, the same thing's true for base. Anything that's an Arrhenius base is an Arrhenius, or is a Bronsted-Lowry base. All right, so look at this one. Here we have two NH3s, and you can see in this equation that one of the H's, the hydrogen ion, is given over here. So therefore, this would be an acid, and this would be a base. And notice that up until this point, all of the ones had, that were Bronsted-Lowry or Arrhenius. Remember we talked about Arrhenius bases, and they always had hydroxides, OH minuses. Okay, this one doesn't have any hydroxide in it, but it is a base because it accepts a hydrogen. Okay, so this is a base. Also, another interesting thing about this is notice that you have NH3, which is both an acid and a base at the same time. Substances that can do that, and there are several, water is another one that does that, is considered to be amphoteric. So amphoteric is a word that means it'd be both an acid or a base. Now, the other thing that they talk about is that for every acid, there's what they call a conjugate base. There's a base that goes with that acid. All right, so the conjugate base is what results when the acid loses the proton. Also, there's a base that has a conjugate acid, And once again, that's because whatever, the base gains or accepts the proton. So let's take a look. Okay. So we know from this is giving away the hydrogen. Okay, so therefore this is the acid. This is the base. Now, take a look at how these kind of match up. So when this gives away its hydrogen, this is what it becomes, right? Okay, so this is the acid. This is the acid over here. The other one is known as the conjugate base. All right, notice that water was over here. This is my base. Therefore, this is my conjugate acid. Okay? They always match up. It's always, the one that it changes into is the opposite. So the acid changes into the conjugate base. The base changes into the conjugate acid. All right, take a look at this one. See if you can figure it out. Stop the video and see if you can figure out the conjugate acid, conjugate base. Okay, so if we go across here and we look, okay, what did it do? Well, we gained this hydrogen, right? That hydrogen went to there. So we accepted a hydrogen, therefore this is a base, this is the acid, and this one over here, because this is the base, what goes with it is the conjugate acid. Therefore this one's the conjugate base. Okay, these two go together. All right, so that's the end of the Bronsted-Lowry acids and bases. Let's just briefly talk about Lewis acids and bases. So kind of be able to define and identify. So Lewis definition, a little bit broader yet, but he defined an acid as a substance that accepts a pair of electrons. Now I always find this confusing because with the Bronsted-Lowry, we said an acid was a donor. It was the hydrogen ion donor. I said donor, no. Okay, but over here we say it accepts a pair of electrons. Okay, so Lewis structures or Lewis acids accept electrons. So let's take a look at this, and this is what it allows you to add in a few other ideas. Like for instance, BF3 would never be considered an acid in any of the other two, but according to Lewis, because there's an empty spot there, it could actually gain some electrons in there, and if there's space for it to gain electrons, then that could be an acid. Same thing with this H plus. Okay, there's no electrons there, so it'd be glad to grab a couple extra electrons if somebody had them, take them. It would then gain electrons. So what we're talking about when we're saying by grabbing them is you've got something like OH minus, which has some, unshared electrons here that it could donate and make that compound here. All right, so that's what they're talking about. That's the example. Lewis base becomes an electron pair donor. So in this example, NH3, we already know that that's a base according to the Bronsted-Lowry one. Well, that's because there's an unshared pair of electrons that it can donate. Therefore, it's a base. Okay? Or over here, we have OH minus, which we kind of drew in the last one there. But it's got some unshared pairs of electrons, which it would be glad to give to maybe this poor little hydrogen over here who's kind of doesn't have anything but a proton. And so then they would form together. So therefore, then this is a base. Okay, so that's really about all you need to know about Lewis acids and bases. Know that they deal with electron pairs. Okay, bases are electron pair donors. Acids are electron pair acceptors. And there you have it. The end.